Hi everyone. I'd like to take a few minutes today and talk about graphing motion. Our objectives, we're going to talk about how we construct and interpret graphs and diagrams for position, velocity, and acceleration. And then we'll see how we can use the slopes and the areas of these graphs to make some calculations, some interpretations of what's going on. So we'll start off by talking about particle diagrams, and these are sometimes known as dot diagrams or ticker tape diagrams. And you can think about these as if you have an oil leak in your car and you drip a drop of oil at a specific interval, the same interval every time. If you looked as your car was moving at what had happened on the pavement later on, looked at that oil drop pattern, you could tell a lot about what your car was doing. That's the point of these diagrams. For example, if your car is moving here to the right and it's giving off that steady oil leak, and when you go and examine these oil drops, you see that they are always the same distance apart, it should be pretty easy to see that this is probably occurring because your car was moving at a constant velocity. Now, what you can't tell from just the oil drops is whether your car was moving to the right or to the left. Have to see the car to do that, but you can tell it was moving at a constant velocity. If instead your car was accelerating to the right, when you were first starting out at low velocity, the oil drops would be closer together. And over time, they get further and further apart as you are going faster and faster, have a higher and higher velocity. Your particle diagram now is non-uniform. So that particle diagram, the ticker tape or dot diagram, shows you a car that's accelerating to the right. Or, however, it could be that your car was moving to the left and it was slowing down. Your velocity was to the left and your acceleration was pointing to the right. Your velocity and acceleration are in different directions, then your speed decreases. Can you think of a case in which the car could have a negative velocity, a negative acceleration, and be speeding up? Well, if you have a car and it's moving to the left, it has a negative velocity, and if it's also accelerating to the left, the acceleration and the velocity vectors are in the same direction. It would actually speed up. Let's take a look now at position time graphs. Let's assume that we have a dog that starts on our back porch. We'll call that position 0. And over time, the dog wanders away from the house at a constant 1 meter per second for 5 seconds. So after 1 second, the dog will have gone 1 meter. After 2 seconds, the dog will have gone 2 meters and so forth. So we get a position time graph that looks like this for the first 5 seconds. Now, the dog decides she's tired. She's going to take a rest for 5 seconds. So she lays down, takes a little nap, and over those 5 seconds, position doesn't change. It remains constant because the dog isn't moving. The velocity of the dog is 0. Now the dinner bell rings, the dog gets excited and comes flying back to the house. So in 2.5 seconds now, the dog is now moving at 2 meters per second. So every 1 second it covers 2 meters of distance until it gets back to its starting point. So the position time graph shows you an object's position is a function of time. But we can learn a lot more from it. If we take a look at the same graph, if we take the slope of this first section of the graph, well, the slope is rise over run. And in that interval, that first 5 seconds, we have a rise of 5 meters. And it takes 5 seconds to do that. That gives us a slope of 1 meter per second. Hey, that's our velocity. So the slope of the position time graph gives you velocity. Between 5 and 10 seconds, during this red interval of the graph, the slope is 0. The slope of a horizontal line is 0, therefore the dog's velocity is 0. And that makes sense. That part of the graph occurred when the dog was laying down taking a rest. Finally, for the ending point of the graph, as the dog comes screaming back to the house, if we take the slope there, that's rise over run again. But our rise, well, we actually have a negative slope, so we have a rise of negative 5 meters. And this all happens in 2.5 seconds, from 10 to 12.5 seconds. or a slope of -2 meters per second, which is exactly equal to the dog's velocity. The dog was going 2 meters per second, but in the negative direction, back from whence it came.